America is making the biggest strategic bet of the 21st century, that whoever wins in artificial intelligence wins the future. But while we focus on the abstract world of intelligence, China is executing a different, far more physical strategy. They are betting that action is the harder, more valuable piece of the future to own. And the means of action in the 21st century are a specific set of technologies we call the electric stack. We're all familiar with the digital cost curves, like Moore's Law. But in the physical world, that same exponential progress has been happening, hidden in plain sight. These were the bulky, inefficient building blocks of the electric stack in 1990. And these are the building blocks of today. The physical collapse in size and cost follows its own powerful curve that we call the electric slide. That slide represents a collapse in cost of an astonishing 99%. More than just a trend, the slide is an engine of economic inevitability. It means that anything that can go electric will go electric, because it's better, because it's cheaper, because it's scalable. And this is where China's strategy becomes clear. Having foreseen this inevitability, they have spent decades capturing the stack. Today, China produces 75% of the world's lithium-ion batteries, manufactures 90% of the neodymium magnets that make motors spin, dominates the production of power electronics, the high-speed switches controlling it all, and is on a national mission to achieve independence in embedded compute, the real-time brains of every device. And while China was cornering the physical world, America's focus and capital were increasingly pointed towards bits, not atoms. The nation's best talent was marshaled to build the abstract world of software and artificial intelligence. As electric stack costs fall and performance rises, new products become feasible. Supersonic passenger flight becomes practical when motors deliver enough power for their weight. Electric planes start to make sense as batteries grow denser and motors grow more efficient. So too will flying cars. Affordable humanoid robots need better batteries, motors, inverters, and microcontrollers more than smarter intelligence. For AI to matter in physical products, they must first be rebuilt on the electric stack. Doing this in the West will be hard, but possible. America still owns the greatest demand and entrepreneurial engines the world has ever seen. We will need to run both at about 1 million RPMs to win this race. Let's start at the beginning with the physics that make electricity and magnetism one story. Electricity can create magnetism, and moving magnets can create electricity. Together, they're one field. Even light is part of it. Electrons carry charge through materials. Put charge in motion through fields and you get force. Wrap that force into a machine and you get controlled motion. Now let's dive into the heart of the electric stack, the lithium-ion battery. To understand the battery's miraculous journey, we first need to understand how it works. Every battery is a dance of chemistry. The anode has too many electrons and wants to give them up. The cathode has too few and wants more. In between is an electrolyte, a barrier that lets charged atoms or ions pass through. It forces the electrons to take the long way around, through an external circuit, powering your device. The story of the modern battery is the search for the perfect materials for this dance. It began at Exxon after the 1973 oil crisis with scientist M. Stanley Whittingham. He created the first rechargeable lithium battery, but his design used metallic lithium, which was unstable. At Oxford, physicist John Goodenough created a new cathode that dramatically increased voltage. The final piece came from Japan, where researcher Akira Yoshino developed a safe carbon anode that solved the explosion problem. But science without manufacturing is just a paper. Sony cracked the code by repurposing their Betamax tape coding machines to produce cells at scale. This led to the battery's first alpha product, the Sony Handycam. Its success created the demand that drove the battery down its cost curve. But the West made a critical error. The MIT spin-off A123 Systems went bankrupt. It was sold for $257 million to China's Wanxian Group. While the West chased high-energy NCM chemistry, BYD made a contrarian bet on LFP. Their own alpha product wasn't a sports car, it was the Humble City bus. Their deep knowledge led to a system-level breakthrough with the Blade battery. Today, with giants like BYD and CATL, China dominates battery development and production. Every modern motor begins with a simple truth. Magnets make motion. When electricity runs through copper, it creates magnetism that can pull a rotor into spin. Around 1820, scientists discovered that electricity and magnetism were one force. Decades later, powerful electromagnets drove the first industrial machines. Permanent magnets provided magnetism that you could carry anywhere. By the mid-1900s, Alnico magnets filled factories, radios, and cars. Ferrite made magnets cheap, samarium cobalt made them strong. When cobalt prices soared, engineers looked for a new recipe. In 1983, a young researcher named Masato Sagawa found we could use neodymium, iron, and boron. At the same moment, John Croat discovered the same compound by another method. Sagawa's version was sintered and strong. Croat's was molded and flexible. Together, they created the most powerful permanent magnet ever made. The same magnets powered drills, cameras, and toys. Adding rare elements like dysprosium made them stable at the high temperatures needed for cars and turbines. In 1997, Toyota used these magnets in the Prius, which offered proof that electric cars could scale. Soon, wind turbines used tons of magnets to turn wind into power. Lightweight drones showed the power-to-weight advantage of Neo motors. Robots, precise, strong, and tireless, used magnets as muscle. Even as demand grew, America sold Magnequench, the factory that made magnets domestically. The deal barred relocation for 5 years, long enough for the Chinese to copy the line abroad. In Tianjin, the same production line started up again. When the American plant closed, production never paused, only moved. Today, China mines, refines, and builds nearly every neodymium magnet on Earth. To control all the electricity and magnetism, you need power electronics. The power electronics that let electricity control itself have grown cheaper and vastly more capable. Their cost has plunged from hundreds to just a few dollars per kilowatt. Early engineers faced limits. A variation called BJT could carry current but switched too slowly. Another type called MOSFET switched fast but wasted energy at high voltage. Engineers wanted a device with BJT strength and MOSFET control. The breakthrough was the IGBT, invented at General Electric by Bjorn Baliga. Japan was the first to commercialize power electronics at scale. Their alpha product was the variable frequency drive. By the late 1990s, IGBTs powered everything from trains to televisions. In homes, they ran compressors, washers, microwaves, and even stoves. Data centers were able to cut power use nearly in half using VFD-controlled cooling. In 2008, Enphase put microinverters on each solar panel, harvesting more energy. Yet switching losses turned to heat, limiting silicon IGBTs. Tesla hit that wall first. Cooling the inverter in the Roadster came at the cost of weight and range. The culprit was silicon's narrow bandgap. Baliga's curiosity led him to explore wider bandgap materials. His equation, Baliga's figure of merit, predicted big gains from new semiconductors. Gallium arsenide came first, but silicon carbide proved far better. In North Carolina, Cree Semiconductor engineers perfected crystal growth, bringing SiC devices into service. Japan Rail's N700A used full SiC MOSFET traction converters. SiC's wide bandgap enabled faster switching and cooler operation. Tesla's Model 3 then used SiC to build a smaller, lighter inverter. Airflow alone kept it cool, boosting range and efficiency. By combining with SiC MOSFETs, Tesla delivered industry-leading efficiency. China moved fast to adopt the same SiC technology that brought Tesla success. BYD's Han and Super E platforms pushed charging speeds ever faster. Next comes gallium nitride, GaN, for higher frequencies and smaller systems. GaN already powers chargers, data centers, and 5G radar. The future belongs to whoever controls these materials. The brain of the electric stack is embedded compute. Not all compute is created equal. GPUs are last in the chain for electrification. Sensors feed compute just like eyes and hands feed a brain. Embedded compute costs have fallen faster than any other layer in the stack. The alpha product for embedded compute was the handheld calculator. Microcontrollers put CPU, memory, and I/O on one chip. A toy called Speak and Spell opened the door to digital signal processing. Digital signal processing powered modems, cameras, audio, and networks. For decades, microcontrollers and digital signal processors worked as a pair until ARM changed the game with efficient RISC designs. ARM's Cortex-M collapsed MCU and DSP duties into one low-power core. In drones, the ARM-based chips fuse sensors and command precise electrical currents. Modern EVs use dozens of these chips through the vehicle. Integrating the MCU and DSP capabilities reduced size, cost, and latency across the stack. The West's lead in this layer is threatened by RISC-V, an open-source instruction set that China is quickly scaling. The path forward for America is to build full-stack capabilities at home, even if it's slow and expensive at first. The history of the electric stack teaches the hard lesson that manufacturing abilities are just as important as scientific breakthroughs. If we don't also control the physical stack, America's focus on AI will be a strategic error. Intelligence without action is insufficient. By racing to build the ultimate AI, we risk commoditizing our strength. Our ideas are instantly manufactured abroad in massive factories. We rebuild not by copying China, but by playing our own game. America's superpower is invention, paired with insatiable consumer demand. The electric slide has made it profitable to once again build in America. We must point our demand engine back at the physical world and restart the flywheel. Demand for better electric products creates a market for domestic component suppliers, like new magnet makers in America. Building these components then teaches us how to innovate the next generation of the stack. We don't need to make everything, just enough to control our own destiny. The two things we thought were different, bits and atoms, intelligence and action, are converging. The physical world is about to be rebuilt. The quadrillion-dollar question is, who will rebuild it?